So, somebody help me out. How did you figure out your class width?
Highest minus lowest.
It's an awesome idea. So class width. So it'll be 72 minus,
54.
and I said everybody use 5 classes, right? So in a quiz or a test, I probably will let you choose your own class size. So everybody's histogram could look a little different. And then here you get
18.5.
3.6, and you always round this up. You don't always have to. It's a really good idea. Because if 3.6 would make the rectangles exactly cover your data, I just need to make sure that all my data points have a place to go, so if I make it a little bit bigger than my actual data ranges, then everyone still has a place to go, right? So even if this came out to be 3.1, I wouldn't round it to 3, because now there's data at the end I wouldn't cover. Does that make sense?
Yeah.
3.1 is necessary. If I make it 3, oh shit, these guys are left out. I got to make a whole other class or something. So you always round that up to the next number. Okay. If you wanted to, if you got 3.1, you can round it to 3.5. If you want to deal with decimals, I'll leave that up to you. All right. So the other place you have some flexibility. So you have some flexibility as far as how many classes to use. You have flexibility as far as how far you want to round this. And then the last piece of flexibility you have is you don't actually have to start at 54. We normally do. But you could start at like 50. You kind of with me? Especially if my class width was 10. Maybe only 50, 60, 70, 80. That sounds good, right? But we normally do start at the lowest. So the book method, the next class would have to start at 58. So this has got to be 57. Oh, like cool. So that looks like it's 3, right? The 54, 55, 56, 57. Oh shit. Well, that's not has nothing to do with it really, but it's just whatever. It's just there. So then now you just add 4 down, and that makes it nice. You always make sure this is 4, because the width is 4, and then finally, and this guy, did I get that right? 4. Yeah. So this should be 73. Some of you guys wanted to make this 72. Doesn't have to be the exact last data point. In fact, it shouldn't be. These should all be exactly the same size, unless I want to make this last one a little bit bigger to suck that last student in. You with me? And it's only going to happen when this actually comes out to be directly a whole number. All right, how are we doing so far? Okay, maybe.
Okay, it would look different if we did your method, though. It would be 54
Yes.
less than or equal to, and it would be 58 at the end.
Yes, cool.
Okay,
These actually mean exactly the same thing, though, right?
okay.
They mean exactly the same thing. Especially because there's no decimal data that I'm working with. Okay, how are we doing so far?
But what if there was?
If there was, this would have to be maybe 54.0 to 57.0. And what that changes is...
If it's like less than 0.5, you still round up? Right?
Just do it one more time.
If it's like 0.5 or something.
Yes, even if it's less than, you still round. You always round up, because if you round down, you're not covering it. If you round up, you're over covering it, but who cares?
No matter what.
You got to cover the data. Real quick, and if I had to make this decimal, the boundary would be 56.95. Do you see that? The boundary always has to go out to the next decimal place out there. And that's a whole other reason to not appreciate this method. I don't want to make that too hard, because I want to make if you guys want to do it the book way, that's fine. You just got to be a little careful with decimals. This way, I don't care about decimals. They're all in there already. They're represented. And then for the rest, it would be 58, X, 62, so forth, right?
But in the bottom, wouldn't it be 70 and 74, not 73?
Exactly.
Okay.
Yeah, this
Just
last
make
number
sure
is
I did it
always
right.
one bigger than that.
Okay.
Yeah, I like it. All right. Okay, cool. So this is the classes. What kind of frequency did you guys get for these?
3.
Yeah, 54 to 57.
2.
Yeah, the only data value in 54 to 57 is 54, right? The next data value up from there is 58. So look back at your data. Even if you did it this way, you got to be really careful if you do it this way. Where does 58 go?
Next one.
Second one, because this is less than 58, this includes 58. That's a really good thing, but it's really easy to make a stupid mistake and put the 58 in the wrong place. Okay, how we doing? Again, this is new. This is new. The math and stuff is not that complicated. It's just freaking new. So you got to let it kind of sink in. Yeah.
Yeah, you know what we said, if we do it out of the book, it's going to be 57 and 58.
Yes.
So I went down by 3, so 57, and then I went to 60.
No.
Why?
How far apart are your classes? 4. So the beginning of this class has got to be 4 away from the beginning of this one. The end of this class has got to be 4 away from the end of this one.
It was different from the last problem because
No, it's the exact same thing we did in the last round. Yeah. So look back at it. Video evidence. That's another reason why I like that. So we look at, I mean, you've got to be able to see the width this way. No matter which way you do this, you see the width that way. The really nice thing about this is you see the width that way too. Okay. Thanks for all super excited about this. And I tell you, the hardest part for me is the fact that they teach this in the book, so I have to address it. I really just want to teach this standalone, but some people just really don't like this. And I want to give you this way to do it. So this would be 1, right? Just that 54. There's no 55s, 56s, or 57s. There's only one thing in that first class. What about the next class? Good. There's a whole bunch of 58s and so forth. So 12. 17. So the next one's 9. So that's consensus. Okay. And then this guy, 2. Okay. All right. Maybe. And real quick, before you do anything else, you just add these up, and they better add up to be 41, or else we're screwed. So, let's see, 13, 30, 41. Yes, thank God. Okay. So what really sucks is when they add to the 40, and you got to go back and figure out who did I forget. All right. So now how do I make the relative frequency? Yeah, this will be 1 out of 41, which is about 2.5, roughly. 12 out of 41. 30%? Nobody objects. I'm just going to keep going, right? You guys, by consensus. 17 out of 41? 41? 9 out of 41? 22? It's like 22 point something or other. I don't know. Okay. And then 2 out of 41? 5%. All right. Makes sense. It's twice that guy. Makes sense. All right. And then you just real quick, what do these have to be? Let's see. 27, 68.
99.5.
98. Oh, let's see. 27, 68, 98. I get 100.5 for what we have up here, which is fine. Depending on how you round it, it might be a little different. Okay, maybe. That's well within the boundaries. We rounded, so it's going to be a little off. Yeah.
Oh, is 99 still up there?
It's just fine. So at the very most, 1% away. So 99 up to 101%. If you're more off than that, you left something out. Or you rounded too much in the wrong direction or something. Okay, cool. How are we doing so far? So again, this is section 2.2. Anybody, before I get too far away from all this, anybody need to see the calculator work real quick? Or yeah. I meant to do that and I forgot. So let's all really enjoy watching me input data. Tell me if something looks wrong. So far, so good. How was your day, honey? Well, we watched this guy standing up there type the numbers into a calculator. How do you think it was? Oh, thank you. All right. They made this calculator way too realistic. It has sticky keys. Okay. Where am I at? Okay, 54. That's all I had through my head. All right, so once you get all the data in, make sure, look, if you go on to the last piece of data, it's in 41st position. Thank God, because I have 41 data points. So it's the very first thing you want to make sure is you got them all in there. Hit stat, sort, enter, and then you tell it which list. So I put it all in list 1. Enter. And then if you go back in, it's in order now. And then, of course, this is how we figured out 54 to 57, I only see one value in there. 58 to 61, I can count. 1, 2, 3, 4, 5. I just count up to 61, right? I think you all get that part. So it's all just how to use a calculator. After that, it's just a bunch of counting. Well, and you make sure it adds up to the right thing so you don't leave anybody out. Make your percentages. And now, how do you make the histogram itself? So I'm going to do it, well, I can do it both ways, really. So what, if I do it the book way, what's going to be here?
53.
Good, 53.5, because that's going to be there. The really nice thing is once you get the first guy, you got everybody. Because now the next one's got to be this far away. That's my class width. Everything is that far apart. So the next one is 57.5. 61.5, 65.5, 73. Okay, good. Take a quick look, make sure you ended up in the right place. What kind of scale, if we're doing a relative frequency histogram, and I might ask you to do either one. This one makes a little more physical sense. You see this one more often, but I could ask you either one. What would my scale look like, maybe? Yeah, you can do 5s or 10s, right? If you want to be a little more precise. 5, 10, 15, 20, 25, 30, 35, 40, 45. You can sound like that if you want to when you do it. So this will be relative frequency. So the only label that would go here would either be relative frequency or frequency if I ask you to make one of those, right? Don't come up with some nifty other things to put there. It's the only 2 options for that. What kind of label do I want down there? Yeah, this is the height of mothers thing again, right?
What?
Was it? Wait, yes. I forgot. Heights of mothers. And then the first rectangle is going to go up to 2.5%. Good, so 2.5%. And then 30%. And 41%. You run into the quiz announcement here. 22%. And finally 5%. Coolness. Well, I meant to say this last time. Remember we talked a little bit about the normal curve? We talked about when the teacher says it's going to curve the grades, they literally pick that thing up and move it. So maybe a C is no longer 70, maybe it's 20. If everybody really did horrible on a test. Does this look normal? Loosely normal, let's say. Starts low, goes high, goes back low, right? It's loosely normal. It's actually decently normal, to be honest, for a small sample.
I thought that the graph had to start on the lines.
No. You definitely want some space here. And in fact, very often you would see this little heartbeat thing to indicate that you jump from 0 up to where your data starts. Just so you're being very honest, you're not skipping any data. This says There was nothing happening before. Let's start here, right? Okay, cool. Okay. How do you feel about that? Now, you got to get in the homework and try it out. It's the only way to really get this stuff down. But in the grand scheme of things, this is one of the easier things you're going to end up doing. So it's just new. But once you get it down, this is pretty simple. This is always the same. Pretty simple. Why would I expect that to be normally distributed? Thinking about what that represents physically, why would I expect that to be normally distributed?
We mostly have average height mothers.
A lot of physical characteristics. In fact, that's where the word normal came from, really, for statistics. What things normally do are in the middle here, and there's just a few outliers. Right? So it's a sense of what's normal. So if I talk about fish lengths or something, and I took a species of fish, and I could see the distribution, there are going to be very few monster fish. Although if you look on YouTube, there's a really freaky video of a giant bass or something eating a shark. It's really neat. Of course, you can see any damn thing you want to on YouTube. I just forgot my train. Oh yeah, so a lot of physical characteristics we expect to have very little overall variation. Most people should be right in the middle. So that's why a normal distribution looks like this. There's a lot of people in here and very few people out there. Okay, so we're going to use the hell out of this thing, especially starting in chapter 6. And then it's going to dominate our life after that. Will be the normal curve. Right? Okay. So I want to do section 2.4. Those of you who have the old edition, the new edition takes 2.4 and 2.5 and puts them together. So the old edition, you got 2.4 and 2.5 separate. New edition, they're together. And what 2.4, 2.5, what they both do is they talk about some other kinds of graphs we could do. We're not going to talk about every single type there is. Thank God. We're going to talk about a few specific kinds. We're going to talk about scatter plot. This is sort of like, and we're actually going to use this example in chapter 10. But if I talk about the number of beers you had the night before, in fact, when I applied for this job, this is the lesson that I videotaped. They required a videotape when you apply for a job here. And some of them like beer, so that's why they hired me. Just so you have less confidence in my abilities. The number of beers you had the night before versus the test grade on this, like a 7 a.m. class. Right? So scatter plot is really just XY. Scatter plot requires two variable data that are linked. So the guy who had, let's say 1, 2, 3, 4, the guy who had no beers, maybe he did pretty well. Kind of with me? But then maybe somebody had 1 beer and they don't know crap anyway, so they're down here. So it doesn't matter how many beers they had, they're going to do horribly, right? So, and then you can just plot. So if I gave you some data, this guy had 2 beers, maybe he's there. This guy had 3 beers, maybe he's there. One guy had 4 beers. Somebody else had 4 beers and they did better. Somebody had no beers and they were right there. You know, so I can just kind of plot points representing the people. I might expect sort of a downward trend, but there will always be outliers. Like, who's this guy? This is the guy that you hate, right? Or girl. Right? Whoever the hell's out there drinking. This is the person that comes in. They drank 4 freaking beers, last night. I'm not talking like a little bit. I'm talking about you. And they come in, and they don't get hungover. Dorks. And they know a lot of stats, so they did fine, right? Or you might have the outlier over here that didn't have any beers, but still failed the damn thing because they don't know, they didn't do any homework, they don't know what the hell's going on. Right? So they really probably should be drinking, but they didn't. So in chapter 2, you're going to be graphing some of these. They're going to give you just a list of data. Right? It's going to be 2 variable data, somehow linked. So this person and this person had so many beers, comma, made this grade. So they have to go together. That's why it's a point. You're going to graph it. Chapter 10, we're going to start talking about, do I see any trends in the data? So if I just populate this thing a little bit more, I might expect a downward trend with some definite outliers in there, right? How are we doing so far? That is called correlation analysis, is regression. And that's some of the coolest stuff there is.
So scatter plots are used for correlation analysis?
They could be. They could be looking at trends, but they don't necessarily have to be. Like there's one problem in the old homework, I can't remember if it was in the new one. You got to plot the energy consumption versus the temperature. So from like 50 to 90, and what you see is this. And why does that make sense? I've got the bottom in the wrong place, but oh well. Let's say that's 90. Why does that make sense? It's energy usage. So this is saying the energy usage goes up when the temperature it goes down or goes up, right? Because in the middle, open the windows. It's nice. Here, oh, it's freaking cold. Over there, oh, it's getting pretty damn hot, right? And those of us who live over, where I live, it's normally nice, but when it gets really hot, because we don't have AC, we don't need AC until it's those certain days. And like, oh, I wish I had AC. All right, how are we doing so far? Okay, all right, maybe. So this would not be a linear relationship. This would be quadratic. This would be parabolic here, right? Okay, maybe. All right, that's later. But for all you got to do for chapter 2 really is plot the points, and then they might ask you, do you see any trend? You just got to describe if there's a shape, if there's a parabolic shape, if there's a linear shape. You just say it after you plot the points.
What else do we use scatter plots for? Besides
You can always talk about trends, but it's really good for pointing out if you're actually plotting two different populations. So if I plotted a whole bunch of data and I got this, that's what I get. I'm thinking, who the hell are these people, and who are these people, and what's the difference between them? Because they don't look like they go together. So this is exploratory statistics. This is where you just collect data, you plot it, and you look at it, and you go, is there something about this that I want to further study? Well, hell yeah, there's something further about this. These people seem to have something in common with each other, and these people seem to have something in common with each other. What is that? Right? Maybe this is cholesterol level versus age or something. And I'm like, where do these people live? Or, that's not a great example, but you guys can see what I'm saying? So you start to wonder, what do they eat? Where do they live? What do they do? Right? Maybe.
So essentially it's allowing you to examine the relationship between two quantitative variables on the same graph?
Look at you. Pretty much. So it's definitely got to be numerical data so you can plot it. Right? So quantitative,
it has to be
a true number. I like it. And you're just seeing if there's any relationship between the two. I like it. Could not have stated it more precisely if I tried. So that's the first kind, scatter plot. They talk a little bit about the correlation coefficient there. That's kind of cool. We're not going to worry about time series graph. It's not really used a lot until you get a lot further in statistics, which we can't here because this is the only level of stats we offer. The next guy up is a nice sounding guy. It's called a dot plot. So look at this. So a dot plot really is exactly what it sounds like. You plot dots that represent some data. So one thing might be batting averages for baseball players on a team. So if I had some batting averages, let's say they're rounded to 2 decimal places to make this easier.
I have a question.
Yes.
Are dot plots similar to box plots?
No.
They're different?
Yes.
Are they similar to stem and leaf?
No.
Okay, they're completely different.
Yes, they're their own little thing. The nice thing with dot plot is it's very quick to do. Right? It works really well for data where there's repeats. So you can kind of see that I'm trying to make that happen. If there are no repeats in your data, you can still do it. It kind of tells you where things cluster. So here's how this works. So I can go from like 0.15 up to 0.4 or so, right? That would capture all my data. So let's see, 0.15, 0.2, 0.25, 0.3, 0.35. That works. Not a very consistent scale, but that's horrible, Jeff. My OCD is going to kick in. Let's see. I don't have, I think you might be able to tell. I don't really have OCD, but I just like to say that. 0.2, 0.25, 0.3, 0.35, 0.4. So make sure your scale is consistent. It covers all the data, right? Whenever you make any graph in here, scale's got to be consistent. And then you start putting up a dot where you see that. So that I see 0.33. Put a dot at 0.33 is about right there. 0.20. Put a dot. 0.17, put a dot. Let's see, it's going to be about right there. 0.17's got 2 dots. 0.36, so forth. I mean, you can see how simple this is. 0.20's got another dot. 0.33, it's got another dot. 0.33's got another dot. So you can kind of see where everything's clustering. Even if I didn't have a lot of repeats, if I didn't have anything around top, I can still see where they were all kind of clustering around. You kind of with me? So that's a quick visual of the data. And if the data was normally distributed, I would expect to see, dot, 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 dot. Maybe something like that. That's roughly normal. Do you see that? So for that really quick made-up data?
Is this a quantitative analysis?
Yeah, because this has definitely got to be numerical, right?
Okay.
Good. The only plot that's not quantitative is that we would look at would be like either a box plot, not a box plot. I'm sorry. What I call a bar chart, but what the book calls a Pareto chart. That doesn't. In fact, they don't even have to be together. That would be like BMWs and Hyundais and so forth, right? That's for qualitative data, or pie chart. Exactly, the percentage that have BMWs, the percentage that have Hyundais, or whatever. So those are qualitative data, right? Just remembering something from chapter 1. Most ones I want to focus on are dealing with quantitative data.
So the difference between a dot plot and a scatter plot would be a dot plot is examining the relationship between a qualitative variable on one plot, or one graph.
Are you talking about a scatter plot versus a dot plot?
Yeah, because
Yeah.
they're very
So
similar.
scatter plot deals with 2 variable data. Dot plot deals with 1 variable data.
Okay.
Right. So if I said this guy has this ERA and he's this old or something, the age in ERA, all right, what was his batting average? I forgot. Age and batting average, then that I could plot it like a scatter plot. This is 2 variables as a part of it. Okay. So stem and leaf. What the book calls stem plot, which just sounds horrible. Stem and leaf sounds better. And you guys are like, I have no opinion on that, Jeff. Whatever you want to say. You can call it whatever you want to. Stem and leaf is actually what it sounds like, which is really, like, what's it sound like? So if I had data where it has, that doesn't range too far, that's probably fine. So the stems of these numbers would be 3, 4, 5. And the leaves would be all the digits that come off of there. So it's kind of like a quick way to organize your data and to get a really quick visual. So 3, 4, 5, those are my stems. My stems. Who gets that? So 3 has what after it? 4, 6, 9. Okay, cool. See how that works? Pretty simple. 4 has 1 and 7. And 5. Let's put this in order. 1, 5, 7, right? And then 5 has 0, 1, 2, 3, 4. If I had another like 54, you'd put another 4 there. You want everything represented, right? And if you turn your head this way, it's almost like a histogram. You can see very quickly it's not normal. Why is it not an official histogram?
There's space.
No. The classes, how many classes are there? 3, and it has to be at least 5, from 5 to 10. So you couldn't use this to make a histogram straight from. But this is a lot quicker than a histogram, and if there are a few more classes, maybe it's normal. I could do this really quick, right? You guys kind of with me? So again, chapter 2, section 2.4 especially, it's not that bad. There's several different kinds of stuff, but the name kind of reminds you what the hell to do to make it. Right? Stem and leaf, stems and leaves. One thing that's missing up here, if I look at this, is this 3.4, 3.6? If I don't have the list of data, I don't know. So one thing you must always have with this is a key. 3.4 means 34. It could mean 304. It could mean 3.4. It could mean 0.34. It could mean a lot of damn things. So once you give me the key, I know what the whole thing is. Now, I love it when somebody gives me a key and they list every single one of these, and that defeats the purpose a little bit. You only have to give me one example that gets me through the whole thing. Right? Okay. That's simple. That's pretty damn simple. Okay. I just wish everything was like that. That's too bad. Let me see. Have I forgot anybody that I want to do? No. Blah, blah, blah. We're not going to do pie charts, really. You should all know about pie charts. We're not going to do ogives. Sorry. It's just fun to say it, but we're not going to do it. And in the old edition of the book, 2.5 was sucked into 2.4, and 2.5 talks about what can go wrong with graphs, or how could somebody misrepresent data to make it look like something else is going on. And I think I talked about this a little bit. If I wanted to show, what you got, Jeff? I don't know. I always have to go to men and women. It's too bad. And I'm talking about their pay rate. And I say, and this is for some specific job. I don't know what job. This is in thousands of dollars. I say men here, the bastards, and the women are there. I desperately want you to understand, there is definitely a difference in the pay rates for men and women. There definitely is. And, that's just the issue that's being talked about for the longest time, actually. And maybe someday something will happen about it. But if you show this chart, you're not doing your argument any good. You're basically telling people, giving them ammunition to say, oh, they're lying, they're a bunch of people that don't know anything. They might use stronger language, I don't know. What's wrong with this chart? No, that doesn't matter, because what kind of data do I have? Qualitative, and the gaps are fine. It's not. There's no scale here that I expect. No, men and women are supposed to be together. Okay, you can talk about that in a different class, but the gap's fine. What's really wrong about this? This is overstated. Why? Because it doesn't start at 0. It doesn't start at 0. So this is roughly 54, right? And then where did I put this? This is roughly 48 or something, 49, let's say. So if I had it start at 0 and go up to 55, let's see, 10, 20, 30, 40, 50, 55, I like it. No, Jeff, that's not how it works, 60. So 10, 20, 30, 40. See, I'm even teaching myself as I'm doing it. So men would go to 40, what is it, 54, and women would go to 49. So the difference is not as, still a difference. But see, this happens so often. People are very passionate about whatever it is they're talking about, and they tend to sometimes make things overstated. The minute somebody realizes you're overstating something, you have lost all the grounds you're standing on. You're gone. You're out. Nobody's going to believe in anything you say anymore, right? You fabricated this. You changed the scale so it looked a certain way. There is a difference. You should have shown this damn picture. And then looked at other professions. Maybe there's a bigger difference in other professions. But the minute you do this kind of thing, you're out. You're no longer in the conversation. Right? And it's too bad because people just get so passionate. They want other people to understand that passion, and that sometimes leads them to fabricate things or mislead people. And that's just too bad. I see that all the time. Okay. So the last little part of the homework is going to reference, they're going to give you a graph, you got to tell me what's wrong with it, and then you got to redo it to make it right. Something else that's a little weird. Box plots are chapter 3. Yeah, I don't think box plots are here yet.
I thought that fell under quantitative.
Oh yeah. But box plots require an understanding of percentiles.
Okay.
And we don't know percentiles yet. Yeah, so that'll be the end of chapter 3. I really appreciate the excitement about getting to it. Because I don't get a lot of people like, come on, where's the box plots? I don't get a lot of people say that about much of anything.
I'm really excited about my box plot.
I like it. What was I saying? Oh, somebody help me out here. If I use a little cube to represent like a little 1 by 1 by 1 cube. Let's say this represents the amount of oil the U.S. used in 1950 or something. And then I say, I have no idea what the real numbers are, actually, I'm just making them right now. Let's say that I say it's doubled by 1970. It's doubled. So I make a cube that's 2 by 2, right? So that I'm claiming that represents a doubling of the amount of oil that we use. Now, what's wrong with that claim? What's the volume of this little cube? 1 unit cubed. I don't know what the units are. No units there, really. What's the volume of that cube? So how many times bigger is this actually? 8 times more. So this is only relevant if there was an 8 times increase over the time. You see? So somebody might say, well, it's twice as big. So maybe 2, 2, 2. Now it's a twice as big cube. No, it's 8 times as big. So anytime you have something with more than one dimension, it sounds a little Twilight Zone-y, but we have 3 dimensions we live in. As long as you don't go past 3, we're all good. So if you try to use a picture of a dollar bill, this is 1 by 1, this is 2 by 2. That's still not twice as big. That's 4 times as big. So you're subtly influencing the way people think when they see your graph. So that is misleading people. And again, it's unfortunate because there might be an argument to make here, but if somebody sees this and calls you out on it, nobody's going to listen to you anymore. You're gone. You're the guy that made that stupid thing. Get away from me. Right? It's too bad for you. Right? Okay. Sounds like I want to make a after-school kind of thing about little Johnny fabricated his data once, and now nobody will listen to him. It doesn't quite follow that format, but oh well. So in section 2.4, or 2.5 for the older editions, they're going to give you a picture of money, and they're going to ask you, what's the problem with this? They're trying to represent some doubling increase, and you say, well, no, because this is actually 4 times as big. How would you represent it to make it right? You could say, maybe I would draw it as a bar graph or some other way. Okay, so you got to say what's wrong with the way they gave it to you, and then make it right. That's what that part would ask you to do. Okay, so allow that to be not too evil. I'm hoping. Now that you see what you got to be careful about when you're reading things. Okay, so that's 2.4 and 2.5 for the old edition. That's about as far as I wanted to make it.
Yay.
Yeah.
Sorry.
I don't take it personally anymore. First year I was teaching, I was like, man, really? Second year, like, oh yeah, go on.
My brain is